In section 7.3, we're going to look at confidence intervals once again. They're going to be a little bit different than what we've seen before, though. In 7.1, we saw confidence intervals for proportions. And we always built our confidence intervals for proportions for the population proportion, P. But in order to say something about the population, we had to actually use the sample to build our confidence interval. So we used our sample proportion, which was P hat, and we found what was called an error. And we took that error and we added it to the P hat to find the top end of our confidence interval, and we subtracted it from our P hat to find the lower end of our confidence interval. And in the background, what was happening is they were using Z values to do all of this. In 7.2, we did something similar. We found confidence intervals for the mean. And again, we were making confidence intervals for the population mean, which is mu. But you don't have the population mean, so you have to use something. You have to use the sample mean, and that's what went in the middle. You still found the error, and you took the error and added it to the sample mean, the x bar, to find the top end of your interval. And you took the sample mean x bar and subtracted the error to find the lower end of your confidence interval. Then what? Well, remember, we actually went over two different types of things you could do in 7.2. You could either use Z's or you could use T's, but it wasn't that you get just to choose whichever one you like better. It was based on whether or not you were given what kind of standard deviation you were given in the problem. If you were given the population standard deviation, sigma, then you used Z's. If you were not given the population standard deviation, sigma, and you were just given a sample standard deviation, S, then we used our T's. Now in section 7.3, we're going to make confidence intervals once again, but this time we're going to make confidence intervals for a standard deviation. And again, we're going to make a confidence interval for the standard deviation, which is going to be a population standard deviation, sigma, except for when we're doing anything for sigma or population standard deviation, whether it's confidence interval or what we'll do later in chapter 8, which is hypothesis testing, we're going to use something different. We can't use Z's, we can't use T's. We're going to use something that is called chi-squared. And the Greek letter chi looks a little bit funny. It looks like a big capital, like curvy X. And when we say squared, it's because it looks like it's squared, but it doesn't actually mean you actually need to square anything. So this is what chi-squared looks like. It doesn't mean you can square anything. It's just a variable. Kind of think about it that way. It's taking the place of Z's and T's when we're doing something for standard deviation. But we'll still have our same setup that we had. We'll build a confidence interval. We'll have something going in the middle. Well, we're trying to make a confidence interval for the standard deviation for the population, so you'll have to use the sample standard deviation, which we use the letter S. And then we'll find our error, which will be on both ends, and we'll take the sample standard deviation S and add the error to get the top end, and we'll take the sample standard deviation S and subtract the error to get the lower end. That's still going to be the same idea, but instead of Z's or T's, we're going to be using chi-squareds. Now, because we're not using Z's or T's, this is going to be quite a bit different because chi-squared is the first graph that is not bell-shaped and it's not symmetric. Let's see what it looks like. The chi-squared graph looks like the following. So here's our chi-squared graph. Notice it does have one special characteristic, is it always starts at 0. However, it does go off to infinity. It does go off forever. So we are going to end up, whenever we're dealing with areas, using for that infinity, just like we did with the normal CDF, we'll end up using a positive 10 to the 99th. However, again, on the left-hand side, we are not going to ever use negative infinity. We're always going to use 0 when we have a chi-squared. So what I would get used to doing whenever you draw your chi-squared pictures is making sure that you draw in a set of axes so that you know you're starting at 0. Also, another more frustrating issue with chi-squared is a lot of this the calculator can't do for us. I know it's frustrating, but that's kind of the way it is. So there is a formula here that we're going to have to know. It's that our chi-squared value, here is what the formula said, our chi-squared value is going to be n minus 1. Remember, n minus 1 is actually our degrees of freedom that we did in the T's. So we are going to start using degrees of freedom as a word again. And then we've got on top our S, which is our sample standard deviation. Notice they're telling us to square it. That means it's just going to turn into a variance. On the bottom, we have our sigma, which is our population standard deviation. Again, they're asking us to square it. And we just talked about this. The n minus 1, remember there's another fancy name for that. That's just our DFR. DF stands for degrees of freedom. A little bit more background on this chi-square distribution. We are going to use this at the end of Chapter 7 and 7.3, and we're also going to use it at the end of Chapter 8. So don't avoid it. It's going to get used over and over again. So chi-squared, we said that a second ago that it starts at 0 every single time. So it can be 0 or it can be positive, but it can't be negative because it starts at 0. It does continue on to the right forever towards infinity. And you're going to get a different chi-square distribution depending on what your degrees of freedom are, your DF. So they'll all look kind of similar. Notice they're always usually skewed where the majority of the graph is on the left-hand side. So I would just get used to drawing it that way. But notice we can end up, if you look at the values for chi-squared that are along the bottom, with some really big numbers, and that's okay. How are we going to find our chi-squared values? Well, we're going to want to find critical values just like we did before for our z's and our t's. When we have our z's and our t's, when we had z's, we definitely used our inverse norm, or you used your standard normal table. When you did your t's, finding your critical values, you did your inverse t, or you used your t distribution table. This time, we are absolutely stuck. We have to use your table. Why there is no inverse chi-squared button on your calculator, I'm sorry, they did not take the time for that. So, when you are testing, you are going to want to make sure that you have a copy of your chi-square distribution table, one way or another. Print it out. Make sure you have something out where you have your chi-squared table available to you. Let's take a look at our chi-squared table, which is right along here in the next page. The chi-squared table. Notice this chi-squared table is actually very special because it's the only table in which we're talking about areas to the right. The normal distribution table and the t-distribution table and the inverse t and inverse norm functions all used an area to the left. This one is the only one that will ever use an area to the right. So, we do need to be careful when we use our chi-square distribution table that we're looking at areas to the right. However, we're going to use it. It's a very, very similar table to what you were doing with the t-distribution table if you used it. You have your degrees of freedom, and then you have your area to the right that you're going to choose. And so you would say, I'm looking for degrees of freedom of 10. And then let's say an area to the right of 0.05, and you would see where those two overlap. And then that would be your chi-squared critical value. But there is an issue. Because your chi-squared graph is not symmetric, you're actually going to have to most likely come up with two chi-squared values. One for on the left-hand side of your picture and one for on the right. Why two values? Because remember, confidence intervals have two sides, a left side, a starting side, and a ending side. So we're going to need two chi-squared values. They're always going to come in pairs when we're doing confidence intervals. So what I'd get used to drawing is something very similar to this next picture, where you are starting your graph at 0 and it continues on forever, and you have some kind of chi-squared value for your left and a chi-squared value for your right. And you may want to write something. Remember, you do get one page of notes, one-sided handwritten. You may want to write yourself a note or draw this picture and write a note saying, remember that the chi-squared table always gives an area to the right. So let's take a look at just how do you find the critical values for a confidence interval. We're not going to actually find the confidence interval yet, just finding the critical values. So they're going to need to give me an n and a confidence level. And I'm going to start by drawing my picture.